Hello, my name is Berg, and our topic was Continual Learning for Automated Audio Captioning using the Learning Without Forgetting approach. So first, few words about Continual Learning in general. So it's also referred to as incremental learning or lifelong learning sometimes. And the goal generally is to get rid of the catastrophic forgetting and to be able to train a model with new data sets without forgetting the knowledge gained from older data sets. And generally there exist three categories, and those are regularizing, which are like regularizer based approaches. And for example, this one, the research here is based on like the learning without forgetting approach is a regularizer. And second was rehearsal, which basically means like replaying old data, either by generating using generators or storing some amount of data. And dynamic architectures is basically uh, dynamically adding or removing nodes in the network, for example. So continual learning for audio captioning. Our goal was to study how a simple continual learning algorithm would help an audio captioning model to adapt to new tasks. And we did this by using two datasets. Clotho was used to pre-train the model. So as a baseline, we had a pre-trained model trained with Clotho, and we further trained it with audio caps. And we evaluated the performance by comparing the performance of simply fine-tuning the model with audio caps to with using learning without forgetting. So for the model itself, we used the Wavetransformer model that was introduced in the Wavetransformer paper from 2020. And it's a transformer-based model that uses the multi-headed attention and positional encoding of the transformer to learn the sequential information to generate audio captions. So for the continual learning method, we chose learning without forgetting, which is fairly simple, regularizing based algorithm for continual learning. Basically, we start by creating a copy of the pre-trained model, and during training with new datasets, we use the output of this copy to calculate additional regularizing loss, which is used in addition to the normal loss term of the model to keep the knowledge of the copied base model basically. And additional lambda parameter is also used to control the strength of each loss term, so how much we want to preserve the knowledge basically. And in our case, we decided that we only consider common words between each dataset. So only the words that were already known from Clotho were considered. So about the results, the first table shows the baseline scenarios that are a wave transformer trained with Clotho and then evaluated on Clotho and on audio caps. Then a wave transformer model that was trained with audio caps and then evaluated with audio caps and on Clotho. And finally, a wave transformer model that was trained with Clotho and then fine-tuned using audio caps, and then evaluated on Clotho and on audio caps. You can see here that when we use the simple fine-tuning approach, the spider score for Clotho degrades from 0.18 to 0.06, so it's a significant degradation on the original datasets there. The lower data table shows the results when we used learning without forgetting and with different batch sizes and different values for lambda. For example, when you look at the scores when batch size was 12 and the lambda was 0.8, we managed to get spider scores of 0.186 for Clotho and 0.157 for audio caps. Compared to the fine-tuning, the knowledge on Clotho was kept significantly better, even though the performance on the audio caps was a bit less, thus learning a bit less on the audio caps, but keeping the original knowledge much better. So finally, we showed that we achieved some degree of continual learning using this method. Even though it was a really simple method, it achieved some degree of continual learning. And as there are like many different newer and more sophisticated continual learning methods, there's lots of future research potential with applying these different kinds of continual learning methods to audio captioning.